Okay, in this problem we're going to combine a situation with friction and with a force acting at an angle. So we'll basically combine two earlier problems we did. We have a block, keeping it simple, and we have friction with the block, but now that block is being pulled with a force at an angle. And we'll stick with the same numbers we've been using. We'll have an applied force of 100 newtons at 30 degrees above the horizontal. So this angle here is 30 degrees. We'll stick with a block with a mass of 10 kilograms. That's about 22 pounds. And we'll stick with a mu, a coefficient of friction, of 0.4. That's telling us the roughness of the ground. If this was sliding with greater roughness, this number might be 0.6 or 0.7. If I had a different material, if this was sliding on ice or Teflon or something, then mu might be a smaller number like 1 or 0.5 or something, 0.05. But we'll stick with 0.4. All right. The first thing is I'm going to draw in my forces. And the usual forces are all here. I've got gravity always acting straight down. I have my normal force acting up. And in this situation, the normal force is not the same as the force of gravity. I have friction acting back. And I have an applied force acting at an angle. Now that applied force is going to contribute some in the x and some in the y. So the first thing I'm going to do after making my force diagram is I'm going to figure out what FAX and FAY are. And remember earlier we said if there's a force acting at some angle that I call F or FA, applied force, and the angle is theta, then this horizontal component is simply the applied force times the cosine of the angle I'm pulling it at. And this vertical force, FAY, is simply the applied force times the sine of the angle. So, if my applied force is 100 newtons, then my applied force in the x direction is going to be 100 times the cosine of 30. Cosine of 30 is 0.866. I'll call it 0.87. And so once again we have 87 newtons of force horizontally. Vertically, I have 100 times the sine of 30. The sine of 30 is 0.5. 100 times 0.5 gives me 50 newtons. All right, I've got everything worked out there. So let's come down and work out Newton's second law in the x and in the y direction. Once again, I'm looking for how much this block accelerates, but there are a number of things I have to figure out first. I'll set up net force equals mass times acceleration, both in the x direction and in the y direction. In x, I have FAX, the applied force in the x direction, minus the force of friction equals m times a. So there's just two sideways forces. The component of the applied force in the x direction minus friction. Now in the y it's getting more complicated here. I have two up forces. I have the part of my applied force that is in the y direction going up. I also have the normal force pushing up, and I have gravity pulling down, and this, like usual, is equal to 0 because we have a sliding motion going to the side. Okay, I'm not going to be able to find friction until I find the normal force. So let me put some things in here. Remember that the force of gravity is mass times g. We'll stick with the same numbers we've been using, 9.8, close enough to 10. So Bernie the block weighs 100 newtons. So I can put in my applied force in the y direction, 50, plus some unknown normal force, minus 100 newtons of weight equals 0. This shows me that the normal force is 50 newtons. I think it was the same last time. Now I come over here. Now that I know the normal force, I know applied force in the x direction is 87 newtons. I know that friction is mu times normal force, and that equals mass times acceleration. So 87 minus mu, we were told, is 0.4. The normal force we figured out is 50, and that equals 10 times A. All right, so I have 87 minus 0.4. 40% of 50 is 20. %40 of 50 is 20, so 87 minus 20, that gives me 67 equals 10A. My acceleration in this problem is 6.7 meters per second squared. So, once again, I started with a force diagram. I draw my forces in all their appropriate directions. Any angled force, I work out the vertical component and the horizontal component by using my trig triangle here. Once I know those components, and once I know the force of gravity, then it's a matter of setting up Newton's second law in x and in y. I put in what I know, and I solve for what I need. Now, the more complicated situation is what happens if there's friction and the block is on an angle instead of being pulled at an angle. So, like a sledding situation, or something sliding down an incline. That's what we'll do next.